Good afternoon. I'm Linda Shapiro, and I'd like to introduce Dr. Ali Farhadi, who's our speaker today. He's in computer vision. He earned his PhD from the University of Illinois, an esteemed institution that some of us may have attended. He is currently doing a postdoctoral fellowship at Carnegie Mellon. Ali does computer vision and machine learning. He's done several different aspects of it, including learning of attributes for object recognition, transfer recognition, all different kinds of recognition, and including object recognition and interested in activity recognition. So I will just let him take over. Thank you.
Thanks, Linda. Thanks for coming, and thanks for having me here. So my talk will be about toward richer representations for recognition. And I'm going to talk about attributes, visual phrases, and sentences. Let me start by showing you this picture and asking you to look at this picture for a bit. So what's going on in this picture? How would you describe it? So this is exactly what we study in object recognition. And if we can get computers to do this for us, that opens up tons of new different applications, ranging from image search, a better image search, navigation, medical applications, media, and lots of different applications. In some of these domains, current recognition algorithms are actually doing really good. For example, character recognitions, reading digits on the envelopes or in checks, or face detection. If you go and buy any kind of camera, digital camera these days, chances are it has a face detector built in. What makes recognition even more interesting, at least to me, is that it's an area that's situated between many wonderful disciplines. It interacts with machine learning, natural language processing, graphics, robotics, systems, cognitive science, computational psychology, optimization techniques, math, stat. So in modern recognition, there are basically two important questions that we're dealing with. Sometimes we're interested in knowing if an example of a specific category appears in an image. So we ask questions like, is there a picture in this? Is there a car in this picture? And the answer would be yes or no. And if so, sometimes we ask, where is it? And that we call it the detection task. Standard way of doing detection is we're going to formulate detection as a classification problem. So we slide a window over an image, and at each window we ask, is there a car in this window? Yes or no? How do we do this? Again, a very standard, straightforward, simple solution is at each, for example, for car, let's assume I want to build a car detector or a car classifier. What I do is I grab training examples for cars. Then I have a way of representing or summarizing the images into features that are called feature vectors. And then I grab examples of the images that have car in them and examples of images that don't, and then I fit a classifier to those. Of course, this is the simplest possible case, and there are many, many more sophisticated methods that does the same sort of thing. What's common between almost all of these approaches is this pipeline. First, we decide on the categories that we want to study. We grab images for them, we extract the features, and then we have several different models to learn those categories. And once those categories are learned, then we can test them on a novel test sets. And the evaluation would be based on how well we can find instances of those categories on novel images. And then we can score it, and as you can see, each year we're just raising the numbers better and better and better. But the main question that I have is this exactly what we want to do in recognition? Just to call things cats and dogs? I believe, personally, there is more to recognition than this. And during this talk, I want to step away from this pipeline. I want to question the input to the recognition system. I want to question the output of a recognition system. And I'm going to show how to tweak the models to do what I want to do with the recognition system. What do I mean by this? If I show you the same picture, so the current target of current setups of recognition is a representation that looks like there is a car in this picture here, there is a horse here, there are a couple of people over here, there is a bicycle over here, then there is a guy and a horse back there. But let me ask the question that I start with. How would you describe this picture? Is this would be the way that you describe the picture or not? So we ask a human subject to describe this picture, and this is what comes out. An old rusty car passing by a cowboy riding a horse, and a person holding his bicycle talking on a countryside road. Let me look into the details of these kind of descriptions. When I showed you this picture, you saw lots of different objects in this image. You saw a car, a person, a horse. There are power poles back then. There are bicycles. There are trees. There are trucks back there. So you saw all of those objects. But when you form your sentence, you select some of those objects, and then you form your sentence. You didn't talk about all of them. You select some of them. And then when you form your sentence, you also describe some of those objects. You're talking about an old rusty car, a countryside road. Also, when the sentence is formed, people are talking about the actions that's happening in the image. There is a car passing by, there is a cowboy riding a horse, there is a person holding a bicycle, and there are two people talking to each other. And also, when we form this sentence, we also talk about the general scene of the picture. This is a road. And if I want to describe it, that would be a countryside road. So compare this very, very rich kind of representations with what we can get with the state-of-the-art recognition system. We get a car, a very tall, huge person over here, a head of a horse, and a huge guy back there. So there is, basically the representation would be a car, person, horse. And compare it with what people can write about this picture. So there is a huge gap between these two representations. There are different levels of understandings of images. And what my goal is, I want to bridge this gap. I want to move toward those kind of very, very rich representations for images. So if my goal is to do that, let me take a very adventurous step, and let me go directly from here to my goal. So if I want to predict sentences like this for images, let's predict them directly from images. So the first step for me would be a direct step from a crude representation that we can get toward the big one. So to study this problem, what we did was basically we asked people to write sentences for images. And we went to Pascal dataset. It's the main benchmark datasets for recognition, and asked people to write sentences for those images. Here's an example of those sentences. Two gentlemen talking in front of a propeller plane. Two men conversing next to a small airplane. Two men talking in front of a plane, and so on. So what surprised us was that people are in amazing agreement on what to say about a picture. All of them are talking about the two men, all of them are talking about the talking, and all of them are talking about the plane and the relationship to the plane. So if such a structure exists, why not predicting it? So what I'm going to do is I'm going to adopt a non-parametric Google type of approach. So one can reasonably do that. So one can go to the space that I have images and sentences in correspondence, and then when a new image comes in, one can match it to one of the images in the data set, and then steal a corresponding sentence. As a result of such a procedure, so for a picture that looks like this, the sentence would be a big house beside a road on an urban neighborhood. Why is this happening? Well, the first reason would be my data set is not big enough. But the bigger reason is that when I'm matching images to images, my matcher lives in the pixel space, and it's not aware of the semantics of the picture. So I want to have a matcher that knows what's going on in the picture. So in ECCV 2010, we introduced this problem of predicting sentences for images. And our solution would be, we're going to assume a representation, a space between the space of images and a space of sentences. And I'm going to call this intermediate space space of meanings. This is an observed space, and I'm going to assume a very impoverished representation for that space. For simplicity, I'm going to represent my space of meanings with objects, actions, and scenes. Now what I can do is I want to learn to go from a space of images to the space of meaning, to go from a space of sentences to the space of meaning. And now if you give me a pair of images and a sentence, then a pair of images and a sentence, then I can project both of them to the space of meaning and score their similarity based on their distance in the space of meaning. So to go from a space of images to the space of meaning, what I do is I run lots of different detectors and classifiers for objects, actions, and scenes, and I couple them with a Markov random field. To going from a space of sentences to the space of meaning, this is a huge problem by itself. And I'm not an expert in that side of the story. So I'm trying to play very safe. I run a parser. I find the main actor. I use something like lean similarity measure to map an image to a sentence to the space of meaning. Now that I know how to map things to that space of meaning, I can score that. Without going to any further detail, here's what happens. For an image like this, the best scoring sentence is a man stands next to a train on a cloudy day. It's surprising that actually such a method works. Since our model is symmetric, I can go the other way around. If you give me a sentence, I can map it to the space of meaning, and I can score all of my images and pick the best scoring one. For example, for a sentence like a horse being ridden within a fenced area, written by annotators on Mechanical Turk, these are the top scoring sentences. I'm sorry, the top scoring images. Since the introduction of this problem, people in different communities really, really liked it. And it started building upon it. People in the vision community started to build better representations to go for images. And of course, people in the language community tried to do a better job on the language side of the story. Let me go back to the examples that I showed you, and let me look under the hood. So the first scoring sentence would be, a man stands next to a train on a cloudy day. But if you look close enough to the picture, you would realize, actually, she's a woman. The next sentence says, a backpacker stands beside a green train, and she's not a backpacker. And if I go down, it's going to get worse. There are two men standing on a rocky beach smiling at a camera. So why is this happening? Maybe I'm asking for too much. Maybe this step that I want to jump from the beginning is just asking for too much. So if that's the case, let me start breaking up the problem to smaller pieces and start to tackle the pieces. When I look at this image, this sentence, so what are the main components of this sentence? Well, when people talk about images, they tend to describe objects. So I want to learn ways of describing things. Instead of saying car, I like to say this is an old rusty car. When people talk about, when people form sentences, they put objects into complex composites, like a person riding a horse, a cowboy riding a horse, a person holding a bicycle. And I want to be able to do these kind of reasonings. So to be able to describe objects, I'm going to talk about visual attributes. And to be able to reason in terms of complex composites, I'm going to talk about visual phrases. For the visual attributes, let me pull another example from my data sets of images and sentences. When we showed this picture to people on Amazon's Mechanical Turk and asked them to write a sentence, people showed different behavior. Do you guys know what is this creature? Okay, so the same pattern happens. Some people on Mechanical Turk, they thought there's a beaver in this picture and wrote sentences like, a beaver on the shore of a stream. It's not a beaver. the nose is in the wrong shape, the ear are just too long, and the fur is different color. Another person thought it's a dog. Honestly, I don't think so. But there are a couple of people who are actually playing a very smart game. They're not sure about the objects. They don't name it. They describe it in terms of things that they're confident about. They're saying that this is a brown, furry animal. Stands behind some plants. A furry animal hides in the bushes. So we people have this amazing capability to talk about and reason about things that we never observed before. If I show you this picture and ask you, what is this? You probably and hopefully haven't seen it before, so you cannot name it. Despite that fact, you still can produce a lot of useful information about this picture. This is a vehicle. Of course, I know it's a vehicle. I can see it. It has wheel. I've seen wheels before on cars, bicycles, motorbikes. It has a wheel. It's right there. And since it's a vehicle that has wheel, it probably moves on the road. You can even push it further. If I have to guess, it's probably something pricey for what you get. It probably works on electrical power. It's not a gas type of vehicle. So there are many, many, many useful information that we people can produce for things that we never observed before. And this is exactly what I want my recognition system to do. I want my recognition system to be able to reason about unfamiliar things. If I show the same picture to the current setups of recognition, what should be the answer? Well, I'm going to get my car and bicycle and motorbike detector, run it over an image, and then the best answer that I expect would be, gee, I don't know what this is. Why is this happening? This is because of this implicit assumption about closed word assumption that we typically have in current setups of recognition. We always assume that the objects to our interest are these 20, 30, 100 categories, and everything that I'm going to be tested on would be these 30 categories. But as a matter of fact, most of the objects that we're going to see are going to be unfamiliar. If I go to a data set in Vision, which is really close to real world, like Brian's Label Me data set. If I go to Brian's Label Me data set and count the number of instances for the top 200 categories in Label Me, this is what you see. So I'm plotting the number of instances for 200 categories. As you can see, the distribution drops very quickly. It's kind of very similar to Piff's distribution. That means that most of the objects that we're going to deal with are going to be unfamiliar objects. How can I build a recognition system that deals with unfamiliar objects? How can I build a recognition system that deals with unfamiliar objects? At CVPR 2009, we proposed a solution to this problem. We introduced visual phrases as a machinery that reasons about objects in terms of shared properties of the objects that we call visual attributes. And we will, at the same venue, at the same time independent from us, another group from Max Planck Institute introduced similar idea. So what our goal was, we wanted to shift the goal of recognition from focusing on naming things to describing things. And now I'm going to show what happens if I do this. So what are the attributes? Attributes talk about properties of the objects. It can be about the material. This is wooden. This is furry. This is made of metal. It can be about the parts of the objects. It can be about the shape of the object. This thing is round. It's cylindrical. It might be even about the function of the object. This thing moves on the road. Or about the pose. This thing is facing to the right and sitting down. To study the problem of attributes, we built a data set called attribute data sets. We went again to the Pascal data set. We asked people on Amazon's Mechanical Turk to label objects in Pascal with 64 different attributes for each object. This is one of the very, very first instances of using crowdsourcing services like Mechanical Turk in vision community. I wanted to study the problem of unfamiliar objects. I also built another data set. I'm going to call them the Yahoo data set. These data sets contain objects from different categories. They're from different categories comparing to Pascal. So here is an example of objects in this data set. For this thing, we have labels like this has metallic surfaces in it, it has glass, it's shiny, it has wheel, door, headlight, and so on. So I want to be able to learn to predict attributes. How do I do this? Well, first, for those of you who are interested in features, what we use, our strategy is we just try to figure our bases, to cover the bases. So what we did was we used color and texture information, we used the famous histogram of oriented gradients, and we used scanning edge detectors, and we just couple all of them together with a spatial pyramid, and then that results in a big feature vector representing my images. And if I want to learn an attribute classifier, what I do is I fit a classifier to examples of images that has that attribute versus of the examples of images that don't have that attribute. And this is what happens. So what I'm showing you is a random selection of the attributes, and I'm showing the performance of those attribute classification problems. For some of the attributes, for example, wheel, it's pretty good. For something, for example, theory, it's above 0.8. And some of the attributes are harder, for example, shiny. But I wanted to use attributes for cases when I've never observed those categories before. This is a test when I'm training my attribute classifiers on Pascal train set, and I'm testing it on Pascal test set. They're not the same images, but images are coming from same categories. So what happens if I get those attributes and test it on my Yahoo data set, which doesn't have any of those categories? So suddenly there's a big drop in my performance. A clear story of overfitting. Let's look at the wheel classifier, for example. There is a big drop. Let me look into more details of what's going on for this case. When I train my wheel classifier on Pascal dataset, it just happens to be the case that all of the images that have wheel in them, they also have lots of metallic surfaces around them. And when I train my wheel classifier in this setting with these examples as positive examples, my wheel classifier might very well be confused with metallic surfaces. So benefiting from correlations is a good thing. In machine learning, we always like to benefit from those. But given the fact that I know those correlations are universal, but when I want to study this cross-category type of generalization, going to a new data set, going to new sets of categories, those correlations do not hold. And if I rely on those, this is what happens. When I get that classifier and test it on Yahoo dataset, which happens to have examples of carriages, they clearly have wheel. It's right there. But there's just no metallic stuff around them. It fails miserably. How can I solve this problem? Well, the standard solution to this would be feature selection. But this is a weird kind of bias because the statistical methods are going to get lost in this dimensionality of this problem. What should I do? So I'm going to make the life of my classifier much easier. What I'm interested in is I'm interested in figuring out which dimensions in my huge dimensional feature actually corresponds to wheel. To be able to do that, and to be able to make life much easier for my classifier, what I do is I go to each category and try to fit a very picky classifier to examples of those categories, for example, cars, with and without wheel. So what I'm hoping for is that all properties of the objects are going to be similar on both sides of this classifier, except the wheel. And then if I fit something like an L1 regularized logistic regression to this case, so L1 regularized logistic regression tends to assign zero weights to almost all of the dimensions and pick very few and assign very few non-zero weights to some dimensions. And those dimensions are going to be the dimensions that are related to my wheel classification problem. So what I do is I go to each of the categories that have will in them, and I perform this kind of feature selection, and each of them give me a selection of features. So those red features would be selected for will, would be related to will inside the car category. I do the same for boat and airplane and whatever that has will in it. And then I grab all of those features and form a really smaller dimensional feature out of those. Now I can go back and train my will classifier with the same data with these features again. And here's what happens. So the blue bars were the case where I train and test in Pascal. The red one was when I use the whole feature. And then the green ones are when I use these selected features. And as you can see, for example, for the will case, there is a big boost in the performance. We're getting close to the case where, as if we are actually training and testing on the same data set. And remember, the green ones are very low dimensional features comparing to the red ones. Now that I can predict attributes, now the fun can start. Now an image comes in, I predict all of my attributes, and that's going to be the space that I'm going to be living in. So if I'm really into naming things, I can learn a category classifier in the space of the attributes. But there is many, many more things that you can do. Not only I can do naming as before, but I can start describing unfamiliar objects. During training, our system never observed any examples of carriages before. And instead of saying, I don't know, it can say, this thing, whatever this is, it has wheel, and it's made of wood. We never observed buildings or tall buildings in our data set. Despite that fact, it can start talking about unfamiliar objects. This thing, whatever it is, it's a 3D box. It has a window. It has row of windows. It actually learned row of window on airplanes and transferred that knowledge to buildings. I can do more than that. I can start talking about typicalities and atypicalities of instances. Assume for a moment that bird category is a category of familiar objects. So I can name it. I can say it's a bird. But I expect birds to have head and beak. When I don't see them, I can actually raise the flag. This is not a normal bird. There is no head. There is no beak. If I see something unexpected, I can report it. So when our system sees this picture, it sees it's a motorbike. But I don't expect to see a cloth on a motorbike. So I can report that. This is an example of a boat. Our system thought it's not typical boat because it doesn't have sail. Clear example of the bias in the data set. Our system thought that this is an airplane, but there is no jet engine. So it's not typical. My favorite lucky example, if you can see it, our system thinks it's a sheep that has no wool. I wish I could have done this. Also, we can report existence of atypical attributes. For example, for the bus case, this is an example of a bus. I don't expect to see faces on buses. When I see it, I can raise the flag. This is an atypical example of a bus because it has a face in it. And that later on, this may result to further inferences about what's going on. Maybe there is a person standing next to a bus. There is even more that you can do with attributes. For a moment, assume that you have never observed goat in your life before. If I explain goat to you in language, I would say goats are something that are made of wool. They're white. They have head. They have horn. They have ear. They're made of wool. So if I describe a goat to you in terms of their property, you can sort of have an idea about what the goat is without being the best goat expert in the world, obviously. But you have a sort of an idea about what the goat is. So attribute-based representation enables the same property for a recognition system. I can learn new categories from pure textual description of that category. You describe a category in terms of its attributes, then I can learn a category. So
in order to do this, you have to label every attribute of every object on the training set.
So the question is, do I need to label in my train set all the images with all the attributes? And the answer is yes, but bear with me toward the end of my talk, and I relax that constraint. So what I'm showing right now is the accuracy of training new categories versus the number of training examples per category. The dotted black line is the performance of attribute-based framework. The solid blue line is the state-of-the-art recognition performance. One observation is that attribute-based representation can learn new categories much faster than standard recognition paradigms. But the interesting point is at 0, where I have no visual training examples for those categories. But if I flip a coin on this side, that would be chanced over here. And my attribute-based representation is this red line over here. So again, it has an idea, sort of an idea about what the GOAT is, without being the best GOAT expert in the world. So some of the assumptions that I have made so far is that I'm assumed that somebody have given me the bounding boxes of the objects when I wanted to reason about them. But when we people look at this picture, without knowing what this creature, what this object is, we can localize the objects. I can say, I don't know what this is, but I know exactly, this is right there. And some of these attributes that are localizable, I can localize. The object is there, and it's well over there. Now I can reason about the properties. So I want my recognition system to be able to also localize unfamiliar objects. How can I do that? Again, I'm going to adopt an attribute-based framework. I'm going to learn a detector for my attributes, and those are going to be all different kind of attributes. I can learn a detector for basic level categories, for superordinate categories, for attributes like parts and everything. Now the procedure looks like an image comes in. I predict all of my attributes for the image. Then I use all of those predictions to first localize the object. And once I localize the objects, then I can start describing the objects. How can I localize an object? Well, since I have multiple different detectors, I can learn detectors and test them on an image. Here's the response of my eye detector. Once I detect the eye, my eye detector by itself has an opinion about where the object is. If I tell you the dog eye is here, you have an idea. You can produce a distribution over where the dog can be. The same story for the head detector. So what I do is I predict all of my detectors over an image, and then go to the space of their votes about where the object is, and cluster that space. And this is what happens. So I use all of my detection responses, I cluster their votes, and get the mean of those responses, and that's what happens. After that, I want to be able to localize the object. And the core idea about localizing the object is that I want to use spatial arrangements of attributes to describe the objects. If I tell you there is an animal whose head is over here, whose tail is over here, and there is some furry stuff in the middle, and ask you which direction the animal is facing, it will be that way. Now, if I tell you that this animal has the potential of having leg, but I can't see the leg, what will be one of the inferences? Maybe the animal is sitting down. So what I want to do is I want to predict all of those detectors in each of those spatial bins. So once I localize the object, I'm going to divide the bounding box of the objects to spatial bins, and I'm going to predict my attributes inside each of those inside each of those bins. Now I can start reasoning about the objects when I say, okay, the head is here, the back is there, so it's probably facing in this way, and I can't see the leg, it should have a leg, so it's sitting down. How can I do this? Well, one thing would be if I can cluster the objects based on the spatial arrangements of their attributes, then I can go to each cluster and infer attributes based on the cluster. For example, all four-legged animals that are standing and facing this way, they're going to have head in this bin, the legs on the bottom, and then the tail over there, and the fur stuff in the middle. And once I know the cluster, for example, a four-legged animal is standing, I can infer properties of those objects. I can say whatever belongs to this cluster can run because they're four-legged, can jump, and stuff like that. The problem is that those cluster assignments and inferences of the attributes given the cluster are going to be uncertain. So how can I do this? So I use a graphical model to represent the uncertainties, and I'm going to solve this problem probabilistically. I'm going to assume a node for spatial parts, meaning that there is a head in this specific bin, there is a leg in this specific bin, and so on. I'm going to assume a node for basic level categories, a node for superordinate categories. I'm also going to assume a node for potentials of the objects having the category, regardless of the part being visible or not visible. So this creature has the potential of having leg. I don't care if the leg is visible or not. I'm going to put a node for function. This thing moves on the road, can run. And I'm going to put a node for aspectual attributes. This is facing to the right, sitting down, and so on. So for some of these attributes, I know how to learn a detector. For example, for parts, for categories, for superordinate categories, I can learn a detector. For some of them, I don't know how to learn a detector. But I know that attributes are correlated. I can guess one attribute by looking at the predictions of other attributes. So what I do is in this graphical model, I let my attribute detectors to talk to each other through a latent route. So what you can think of the route as a multinomial distribution, as an index of the cluster number 1, cluster number 5, and so on. So I'm going to call the categories for which I can build a detector A, and the categories of attributes, and the set of the attributes for which I cannot learn a detector B. So as for a moment, assume that I learned this graphical model. Then I can actually do inference in this graphical model. If I'm interested in any of these attributes in the category A, so I'm going to predict all of my attributes, and that will be observed, the D bar. And I'm interested in the probability of, let's say, attribute AI given the D bar. And I can approximate that by marginalizing over the root, which is a multinomial over these clusters that I talk about, the probability of each attribute given the root, and the probability of the detection given the attributes, which I'm going to flip. Also, I need to marginalize over all other nodes. I can do the same with the category B, with the difference that I don't need to include these here, because I don't have a detector for them. So this is what happens when I run this. Before actually showing this, the way that I solve the graphical model is by simple EM. So I'm going to assume a first assignments of R's, basically assignments of the clusters. I'm going to learn those probability estimates, probability of R, probability of A given R, and so on. And then I'm going to use those probabilities to re-estimate R and iterate as I go. So here's an example of what I do, what routes these route model can find. So the first route that this model discovered is examples of animals that have leg on the top and head on the bottom. The second route would be examples of four-legged animals that have leg on the bottom and also head on the bottom. They're eating something from the ground. And route number 6, for example, would be examples of four-legged creatures that are running to the left. So these are the type of routes that it can find. Now that I can find routes, I can start predicting attributes. So the first thing that I'm going to evaluate my system on is how well I can localize objects. And the first step on that is how well I can localize familiar objects. So what I'm showing here is the performance of the state-of-the-art detection responses, which is the dotted red curve, and the attribute-based framework, which is a solid red curve. So observation number 1 is that adopting this attribute-based framework also helps localizing familiar objects. But the interesting part is when I can localize unfamiliar objects. So our system can localize things that it never observed before, with this much accuracy, very close to the accuracy of localizing familiar objects with the state-of-the-art recognition methods. Here are some examples. On this picture, with 3 elephants on them, so we've seen elephants during training. We know how do they look like. We can train models for those. And instead of just saying elephant, 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 we can produce this much of information. We can localize the elephant, saying that this is an animal, it's a mammal, it has leg, here's the leg, here's the trunk, here is the foot. This is a 4-legged mammal, and I know it's an animal, it's an elephant. But it gets way more interesting when I show our system an image of an unfamiliar category. Our system never observed cats during training. Despite that fact, it can localize this as an animal, which is a mammal. Here's the head, here's the leg, and of course, it has hump. Our system never observed any examples of jet skis before. Despite that fact, it can localize it as watercraft. Same story with the bus. We never observed bus during training. We can localize it as a wheeled vehicle. Here is the wheel, and here is the license plate. This is my favorite example. We never observed carriages on horses during training. But look at how much information we can provide for this picture. We can localize the carriage as a vehicle, saying that this is a vehicle, this thing, whatever it is, has a wheel, and this thing, whatever it is, moves on the road. Without ever seeing any example of horses, we can localize the horse as an animal. Here is the head, here is the leg. This creature is a 4-legged mammal. It can run, can jump, and it's facing to the right. Since the introduction of attributes, people in the recognition community really likes the idea. And people have started to building upon it, adopting it to different problems in motion capture, in human activity recognition, and lots of many different domains. Niraj, for example, he's a pioneer on attributes and faces. Let me step back again and look at my goal one more time. I wanted to predict sentences for images, those kind of very rich representations. And we were at this point, car, person, horse. Now that I have attributes, I can start describing objects. Now I can go one step up and talk about an old rusty car, a person, and a horse. Now I can go to the second part of the problem and start learning about complex composites of the objects. How can I start detecting a cowboy riding a horse or a person holding his bicycle? How can I do that? How can I detect complex composites of objects? So if I ask this question from a recognition person, the conventional wisdom would be detect the person, detect the horse, and then sort of reason about their relationships later on. Despite being combinatorially very well behaved, there is a big problem with this approach, which is the appearance of the objects may profoundly changes when they participate in relationships. A person riding a horse does not look like a typical person. A horse being ridden by a person does not look like a typical horse. And my horse or person classifiers fail to detect it. So what should I do? So if you look, there is this whole spectrum of elements of recognition. For years, we just take it for granted, we just took it for granted that objects are the center of a recognition paradigm. We want to detect objects, objects, objects. Sometimes we want to actually go from smaller elements and talk about attributes and parts. And sometimes we go all the way to the whole image and talk about scenes. So what is the right quanta of recognition? Is it objects, attributes, scenes? So at CVPR 11, we introduced visual phrases to cover the gap between objects and scenes. So visual phrases are the chunk of an image corresponds to a chunk of a meaning bigger than a word. We typically need to describe a visual phrase with more than one word. which would say a person lying down on a sofa, a person drinking from a bottle. Similar to definitions of objects, attributes, parts, there is no crisp definition of what is exactly a visual phrase. One way to think about it is visual phrase is a part of an image that's natural to cut out. So if I show you this picture and give you a pair of scissors and ask you to cut the main actor out of this picture, what would you cut out? Would you cut the person riding a horse as one entity or just the horse? So the rider and the horse belong together as one entity. And it's so unnatural to try to separate them from each other. And of course, this relationship does not hold for all combinations. The horse and the sign over there, they don't belong together. Practically speaking, ironically, it is much, much simpler to detect a visual phrase as one entity instead of detecting the components and then join them up. Why is that? Because when objects participate in relationships, they expose such a characteristic appearance that makes detecting them as one entity way simpler. When people drink from bottle, they expose such a characteristic behavior and appearance that makes detecting them much, much easier than detecting the person and then dreaming of detecting the bottle. So what I propose is to add visual phrases to our vocabulary of recognition. I want to detect a person riding a horse, the dog lying on a sofa, the same way that we detect the person, the dog detector. Well, but there are two immediate reactions to this proposal. Well, there are a combinatorial number of phrases that I can make with any given set of objects. But I'm not proposing to build a model for all possible combinations of the objects. There are some combinations that actually make a visual phrase, and there's no excuse not to include them in our vocabulary of recognition. There's another issue with this proposal, which is the number of training examples dramatically decreases as I increase the specificity of the visual phrases. There are more examples of horses than person riding a horse, than person wearing a blue jean riding a black horse. But because of this characteristic, this unique appearance of visual phrases, we actually don't need that many training examples to detect a visual phrase. Here's an example. For this picture, the state-of-the-art person detector, when I actually applied it to this image, finds only one instance of a person. When I took the state-of-the-art bicycle detector and ran over this image, it manages to find no instance of bicycle. Whereas when I run my person riding a bicycle detector, it actually finds 5 instances of people riding bicycle. For these two fellows enjoying their time on the beach, the person detector finds 2 instances of people. The bottle detector has no clue about what's going on here. But the person drinking from bottle detector actually finds the fellow. So you might have seen this picture. This is an example from our paper and our data sets of visual phrases. So let's see how they work. So I want to measure the accuracy of how good I can localize complex composites like visual phrases in images. So what I'm showing you is the performance of the localization. The blue curve up there, which you hopefully can see, is the performance of the visual phrase detector. And then the red curve down there is a baseline that works as an optimistic upper bound on how well one can predict a visual phrase from predictions of its components. And look at the huge gap between these two curves. They're not even comparable. The way that you can detect a horse and rider jumping is not comparable to this curve down there. You can't probably see it. It's so close to the 0. Why? Because when people ride horses, they have very characteristic posture that a person detector cannot find it. So visual phrases are wonderful entities to be added to the vocabulary of recognition because they're really easy to detect. But also, they can help detecting other objects. So the story looks like an image comes in, I run all of my detectors, including objects and visual phrases, and each detector has an opinion. For example, the person riding a horse detector thinks there is an instance of a person riding a horse in this red box. The green box over there is the person detection response that thinks there is a person there. So if there is a detection of a person riding a horse and a detection of a person, there's got to be a horse somewhere. I want to push the horse prediction up because of those two things. And if that's correct, I should get rid of those two wrong person detection up there. So we introduce an algorithm called decoding that looks at all of the predictions and decides on what goes to the output of a recognition as a response. For example, this is as an output of the method. This is basically a classical structure prediction problem that you can try to learn to reweight bounding box predictions against each other. For example, there is a strong dog-lying sofa prediction here. There are four wrong person predictions. This strong dog-lying on a sofa prediction manages to convince the decoder to push a sofa prediction and got rid of a person prediction. You might think, actually, why on the earth we would predict a person right in here? But because we look at the picture, and if you look at the space of the features, the space of the hog detectors, that looks really like a person. Because there are strong edges over here that you might not see. There is a round thing up here that looks really like a person. But a decoder can get rid of those wrong predictions and pushes up a sofa prediction. There is a person riding bicycle prediction, 1, 2, 3 wrong person predictions, and a correct bottle prediction. And then the decoder forces those predictions to push up a bicycle prediction. So what I've talked about so far is going from object categories to a representation that has a description of the objects. Now I can go one step higher. Now I can reason about complex composites of the objects. A person riding a horse, a person holding a bicycle, another person riding a horse. And this is just the beginning of this story. There are still many, many, many more steps to be taken. One of those steps that I want to take is an answer to Pedro's question. When I decided on the attributes, I was the guy who injected the semantics, and I said, okay, the vocabulary of the attributes should be wooden, fairy, has will, and so on. But there's no reason for this. So I'm developing methods that can discover attributes automatically from the data. And then the next question is, where is the place that I should inject the semantics? Is it when I decide on the vocabulary of the attributes, or I can predict those things and then ask for semantics? These things are round. These things have checkerboard pattern. People can easily name them afterward. Another thing that I'm pursuing is to get away from the bounding box representations. I want to, why? Because when I present objects with the bounding box, I have no clue where the object is. If I poke this pixel, is that going to be the horse or not? So when I go to a fragment-based representation, a region-based representation, when I automatically build a huge pool of object regions, and then when I build this, I can start doing lots of different things. I can do classification by transferring the labels. If this region matches to 3L plane, so it's going to be an airplane. And then I can do object transfer or image manipulation. But when I match things, I'm always assume that I know objects are similar. When we say in recognition, objects are similar, we just typically have one way. We say these objects are similar, without saying in what sense. And if I don't know what are the senses of similarities, when I want to transfer the knowledge, I don't know what knowledge to transfer. So these objects are similar to that object in terms of having a fence. And these objects are similar to this object in terms of having a wheel. So I'm developing methods to understand and to infer the senses of similarities. I also, toward longer terms in the future, I want to be able to reason in semantic spectrums. I want to be able to use all of those things that are hanging in the air, attributes, poselets, parts, objects, visual phrases, scene, and put them in a unified framework to reason about the objects. Also, I want to do knowledge selection. I want to know what to report. as an output of a recognition system. I can predict all of the attributes of the objects. But which of them are actually worth mentioning? There are, of course, things that I didn't talk about. If you're interested in any of those things, I'll be delighted to talk about them. So with all of that, I conclude.